Welcome back. Problem 1-81. This problem is taken from chapter number 1, that is stress, and book name is Mechanics of Material by RC Hibbeler. So statement is the steel pipe is supported on cylindrical base plate and concrete pedestal. If normal failure stress for steel is 350 megapascal, determine the minimum thickness T of the pipe if it support the force of 500 kilonewton. Use a factor of safety against the failure is 1.5. Also find the minimum radius R of this base plate so that minimum factor of safety against the failure of concrete due to bearing is 2.5. The failure bearing stress for concrete is 25 megapascal. So you can see this is the pipe having axial load of 500 kilonewton. The outer radius is 100 millimeter and inner radius is not known, and thickness T is also not known. And this is the base plate that is mounted on this concrete base. Clear? So we have been given all the data, so you have to find this thickness T and minimum radius R of this base plate. So let's start with the solution. We can see we have steel plate and concrete. So we know that allowable normal stress for steel is equal to this load, which is acting as 500 P divided by the area of this pipe. Okay, clear? Area of steel pipe. And similarly, allowable bearing stress for concrete is equal to this load P divided by the area of this concrete. So area of this concrete is similar to this area of this base plate. So area of concrete, you can see. Okay, now what we will do is that we will find this as area of steel. This is equal to P, and area of this pipe, hollow pipe, will be equal to pi by 4 or pi r outer square minus r inner square. Clear? And similarly here, this will give you allowable stress in steel, and allowable stress in concrete is equal to P divided by area of concrete. So which will be the same for this base plate, so it will be pi r square. Clear? So it will be pi r square. Now we will calculate this allowable stress in steel and allowable stress in concrete. So we know that for steel, first I will calculate for steel. So for steel, we know that factor of safety is equal to failure stress, clear, allowable stress in failure divided by allowable stress working. Allowable, what I have written, let me correct it. In failure stress in steel is equal to allowable stress in steel. So factor of safety for steel is given as 1.5. So we are finding allowable stress. So allowable stress in steel, which is allowed and will be safe, will be equal to failure stress in steel divided by factor of safety. And that will be equal to 350 megapascal divided by 1.5. And this will give you 233.3 megapascal in steel. Clear? So I will write it. We get allowable normal stress in steel is equal to 233.3 megapascal. Now for concrete, we have also the same formula, which is that factor of safety is equal to failure stress in concrete divided by allowable stress in concrete. So from here you will get allowable stress in concrete is equal to failure stress in concrete divided by factor of safety. So put the value. Allowable stress is 25 in concrete and factor of safety is 2.45. So I will write 25 divided by 2.5 will give you 10 megapascal. Clear? Concrete. Now what we will do is that we have this value, we have this value, we have R naught. So we will calculate for steel. So let me choose another color. For steel, we know that allowable normal stress for steel is equal to P divided by pi into R naught square minus RI square. So this is RI square. This is 233.3. Allowable normal stress is 233.3 megapascal. So 10 to the power 6 is equal to P is given as 500 kilonewton. So I will write 500 into 10 to the power 3 divided by pi and R naught, which is 100 millimeter. So R naught is 100 millimeter and in meter it is 0.1 meter. And RI is not known. So this is RI. Clear? So 0.1 square minus RI square. So from here you will get pi into 0.1 square minus RI square is equal to 500 multiplied by 10 to the power 3 divided by 233.3 into 10 to the power 6. And we will get pi into 0.1 square minus pi into RI square is equal to 500 into 10 to the power 3 divided by 233.3 into 10 to the power 6. So what we will get is that pi into 0.1 square minus this value 500 into 10 to the power 3 divided by 233.3 into 10 to the power 6 will be equal to pi RI square. And if you divide RI on pi on both sides, clear, so you will get 0.1 square minus 500 into 10 to the power 3 divided by pi into 233.3 into 10 to the power 6 will be equal to RI square. And if you take under root on both sides, so RI will be equal to 0.09653 meter. So in terms of meter, it will be equal to millimeter, it will be 96.53 millimeter. Now you have RI. So we know that RI plus T is equal to R outer. Let me show you here. You can see RI. This is RI and this is T will equal to R naught. So you can put RI is 96.53 plus thickness is not known and R naught is 100 millimeter. So thickness will be equal to 100 minus 96.53 millimeter. So from here you will get the thickness of this steel pipe is 3.47 millimeter. So this is the answer of our first part. Now we'll move towards second part, and in second part we have been find the radius of this base plate. Clear? So we know that we use this formula, and allowable concrete is 10 megapascal. So we know that allowable stress in concrete is equal to P divided by pi R square. So from here this R square will be equal to P divided by pi into allowable stress for concrete. So put the value P is 500 kilonewton. So 500 into 10 to the power 3 divided by pi, and allowable stress is 10 megapascal. So 10 into 10 to the power 6 will be equal to R square. And when you take under root on both sides, square root. square root on both sides. So you will get this as r will be equal to 0.1262 meter, or this r will be equal to, in millimeter, it will be 126 millimeter. And that is the answer of our second part. So that was all about this problem 1-81. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. And I will request you to share these videos with your friends and help me in growing further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-77 that is taken from chapter number 1, stress, and book name is Mechanics of Material by RC Hibbeler. So statement is the tension member is fastened together using two bolts, one on each side of the member as shown. Each bolt has a diameter of 0.3 inch. Determine the maximum load P that can be applied to the member if allowable shearing stress for bolt is 12 ksi and allowable normal stress is 20 ksi. So you can see this is member 1 and this is member 2 that are held together by using a joint having bolt on one on each this side and other one on the other side. And this is exerted by a tensile load P. So you have to find the maximum load or allowable load P that can be applied on this joint or on this tensile tension member. So let's start with the solution. So what will be the first step is that first step is if you cut this or if you separate these members and draw the free body diagram. So it will be like this. Let me draw it first. This will be member. You can see this is a load P, clear, and this angle is 60 degree. So when you separate it, so you will be having a normal force perpendicular to this surface, clear, and this will act that we take it upward, and there will be a shear force on this surface, clear. This will be a shear force. This is V and this will be equal to normal force. So we'll find this normal force and V in this member, because you can see that this normal force, this shear force will tend to shear this bolt, and this normal force will cause the tension in this bolt. So based on these two criteria, we'll find the maximum load that can be applied on P. So we will find this equation, N and V by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along Y direction must be equal to 0, and Y direction is taken in this because you can see you have N in this direction and V is in this direction. So what we are going to do is if you draw a line parallel to this 60 degree, clear. So if you draw a line parallel to this 60 degree, so this P will have two components, one along this axis which is equal to one along this axis and other along this parallel to this N. So this will let this is equal to X component and this is equal to Y component. So you can see Px will be equal to P cos of 30 degree, P cos of 60 degree, clear, and this Py will be equal to P sine of 60 degree. And you can see when you apply this equation, so you can see the force in this direction is N and other force in this direction is Py, which is equal to P sine of 60. Their sum must be equal to 0. So I will write N minus Py, which is P sine of 60 degree, clear, is equal to 0. So from here, this N will be equal to P sine of 60 degree, clear, and this P will be equal to N divided by sine of 60 degree. So that will be equal to 1.1547 N times N, clear. So I will write it P will be equal to 1.547 times N. Let this is your equation number 1. Now we will apply another equation that sum of all component in X direction must be equal to 0 and force in this direction is taken as positive. So you can see V is in this direction and Px is in opposite direction. So plus V minus Px is equal to 0. So I will write V minus Px is equal to 0. So we know that Px is P cos of 60 degree, clear. So from here that is equal to 0. So V is equal to P cos of 60 degree, clear. And P will be equal to V divided by cos of 60 degree, and that will be equal to 2 times V. So I can write P is equal to 2V. That this is your equation number 2. Now you can see that here P is based on the normal force and here in 2 it is based on shear force. So what we are going to do is that we will first apply a criteria. We will apply criteria based on allowable shearing stress. Allowable shearing stress. So we know that allowable shearing stress is equal to V divided by area, since there are two bolts, one on this side and other one is on another side. So we will take this V. V is equal to we do not know V, so clear, I will write V divided by 2 bolts, so 2 multiplied by pi by 4. Diameter of bolt is given as 0.3 inch, so I will write 0.3 square. And allowable shearing stress for bolt is 12 ksi, so I will write 12 into 10 to the power 3 is equal to V divided by 2 will cut with this, so we will get pi by 2 into 0.3 square. And from here we will get V is equal to 12 multiplied by 10 to the power 3 multiplied by pi by 2 into 0.3 square. And you will get the shear force comes out to be 1.696 kip. Now you have this V, so put it in equation number 2. Put in equation 2. So you will get P is equal to 2 times V, and that is equal to 2 multiplied by 1.696 kip. So you will get this P will be equal to 3.39 kip. Now this is the tensile load based on, it is based on shear stress, allowable shearing stress. Now what we will do is that we will use, this was the first criteria, we will use second criteria based on allowable normal stress, and we know that allowable normal stress is equal to normal force divided by area. Since there are two bolts, so I will write N divided by 2 multiplied by pi by 4. Diameter of bolt is given as 0.3, so 0.3 square, and allowable normal stress is given as 20 ksi. So 20 into 10 to the power 3 is equal to N divided by pi by 2, 0.3 square. So you will get this N will be equal to 20 into 10 to the power 3 multiplied by pi by 2 into 0.3 square, and you will get this N will be equal to 2.827 kip. Put n is equal to 2.827 kip in equation number 1. And what is equation number 1? P is 1.547 times n. So P is equal to 1.547 multiplied by n. So 1.547 multiplied by 2.827 kips. You will get P is equal to 3.26 kip. And this P is based on, normal stress. There. So here you can see we have two values. One P is this one and another one is this one. So this largest load, I will write it over here. The largest tensile load, largest P, which can be applied on this system is 3.26 kips, and which is the answer of our this question. Why we have selected this smaller one and called it as the largest load? Because you can see this load is less than this, so it will be safer. And if you put this P in this formula, and then shear force in this formula, so it will exceed the allowable, your shearing stress will be greater than this allowable shearing stress. So therefore, for safer design, we use P is equal to 3.26 kips. And that was all about this problem 1-77. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos in your community so that my channel may grow further and most of the students may learn from my videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 1-75 that is taken from chapter number 1, Stress, and book name is Mechanics of Materials by RC Hibbeler. So statement is the hanger support the joist uniformly so that it assumes the 4 nail on each hanger carries an equal portion of load. If the joist is subjected to loading shown, determine the average shear stress in each nail of the hanger at an A and B. Each nail has a diameter of 0.25 inch and the hanger only supports vertical load. So you can see this is the joist that carries the load shown over here, and these are the hangers A at A and B that supports it. Now in this hanger we have 4 nails, 2 on this side and 2 on other side. Similarly, 2 nails on this side and 2 on other side. So diameter of nail is given, so you have to find the average shear stress at the nail at end A and B. So let's start with the solution. So as if we remove this hanger support at end A, so you will be having a reaction force, let this is FA, and if you remove this hanger support at B, so you will be having a reaction force which is FB. So we'll find this FA and FB and then we will solve this. So how we'll find this FA and FB? By using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0 and taking the counterclockwise moment as positive. Here you can see that this is the load 30. So if I draw a horizontal line from here, so we will convert this load into a uniformly distributed load, plus there will be a triangular load as well. This will be the triangular load. You can see this will be the triangular load. So here this difference will be equal to 40 minus 30 will be equal to 10 pounds per feet. Clear? So what if we convert this uniformly distributed load into a point load? So it will be equal to this 30. Clear? So 30 multiplied by length over which it acts. So 30 into 18, which will be equal to 540 pounds. Now we will convert this triangular load into a point load. So this you can see this is a triangular load. Here magnitude is 0 and here the magnitude is 10 pounds per feet. So what if we convert this triangular load into point load? So it will be equal to, I will write it over here, it will be equal to 1/2 into this 10, which is the magnitude, and length over which it acts is 18. Clear? And that will give you 90 pounds. So 90 pounds will act. And what about its location? So its location from B point will be L by 3. So L is 18. So 18 by 3 is equal to 6 feet from end B. So this distance will be 6 feet. And what about this uniformly distributed load? So it will act at the half. So this distance will be equal to 18 divided by 2, which is equal to 9 feet. And we will left with this 3 feet as well. Now we'll find this FB by using equation of equilibrium, that sum of all moment about point A is equal to 0. So you can see first moment, this force is passing through this point A, so it is not producing moment. So first force which is producing moment is this force, which is 540, and perpendicular distance is 9 feet, and this is producing clockwise moment, so it will be negative. So I can write minus 540 multiplied by 9. The second moment will be due to this load, which will be 19 pounds, and now perpendicular distance is 12 feet, and this is also producing clockwise, so it will be negative. So I will write minus 90 into 12. And the last moment which is produced due to this FB force and perpendicular distance is 18 feet, and this is producing counterclockwise moment, so it will be positive. So I will write plus FB into 18. And the sum of all moment about point A must be equal to 0. So from here you will get 18 FB is equal to 540 multiplied by 9. 540 multiplied by 9 plus 90 into 12. So from here you will get FB will be equal to 540 multiplied by 9 plus 90 multiplied by 12 divided by 18 will give you FB. And FB, when you calculate it, this will be equal to 330 pounds. Now you have this FB, you can find FA by using equation of equilibrium. So what is the equation of equilibrium? Is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So 4 forces, these 2 forces are upwards and these 2 forces are downward. Their sum must be equal to 0. So FA plus FB minus 540 minus 90 will be equal to 0. So I will write FA plus FB is 330 pounds minus 540 minus 90 is equal to 0. So from here you will get FA minus 300 will be equal to 0 and you will get FA will be equal to 300 pounds. Now you have FA is equal to 300 pounds and FB is equal to 330 pounds. And you can see that there are 4 nails over in this support. So this reaction force acts vertical on this, which is causing shear in this nails. Clear? This force causing shear in this nail. So what we will do is that for nail A, I will write for nails at A. We know that we have been given as diameter of each nail is 0.25. So we know that shear stress at A will be equal to FA divided by as area. Clear? Area. So area at A. So this is for single nail. single nail. For 4 nails, as there are 4 nails, we will get the shearing stress at A will be equal to, or in nails A will be equal to FA divided by 4 times area of nails. So FA divided by 4 into pi by 4 diameter of nail is given as D. So D square. So put the value FA is 300 divided by 4 multiplied by pi by 4 into D square. So diameter is given as 0.25 inch. So I will write 0.25 square. Clear? So after solving that, you will get the shearing stress at point A will be equal to 1528 psi. Or shearing stress at point A or in nails at A will be equal to 1.53 ksi. Now what we will do is that we will move toward for nails at B. So shearing stress at point B will be equal to vertical force at point B divided by, there are 4 nails, so 4 times area of nail B. So again FA divided by 4 multiplied by pi by 4 D square. This is B. What about B? So FB is 330 pounds. So 330 divided by 4 multiplied by pi by 4, and D is 0.25 because the diameter of each nail is 0.25 inch. So when you calculate it, you will get the shearing stress in nail B, in single nail B, will be equal to 1681 psi. Or you can say the shearing stress at nail B is equal to 1.68 ksi. Ksi means kilo pound per square inch, which is the answer of our this question. And that was all about this problem 1-75. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and thank you for supporting me. Take care. Welcome back. Problem 1-80. This problem is taken from chapter number 1, that is stress, and book name is Mechanics of Material by RC Hibbeler. So statement is the thrust bearing consists of a circular collar A fixed to a shaft B. Determine the maximum axial force P that can be applied to the shaft so that it does not cause the shear stress along cylindrical surface A or B to exceed allowable shearing stress of 170 megapascal. So you can see this is the thrust bearing, cylindrical thrust bearing, or circular thrust bearing, and this is collar A, which is fixed with the shaft B. Clear? And there is axial load along the axis is applied on this shaft, and it is given that at B, cylindrical surface B and A, the stress should not exceed the 170 megapascal. So you can see that due to this force, there will be a shear force in that will occur at this region, clear, because it will cause it to shear this portion, and due to this axial load, it will also cause the shearing in this region as well. So we'll find the maximum load that can be applied so it does not exceed the allowable shearing stress of 170 megapascal. The data is already given, so let's start with the solution. So we'll calculate this P based on shearing stress along A. So you can see that due to this load, there will be a shearing at A. So this shearing stress will be equal to, we know that allowable shearing stress is given, which is equal to P divided by shearing area. So what will be the shearing area? So you can see this is a cylindrical surface, clear? So at A, this area will be equal to this diameter. Pi into D will be the circumference of this portion, clear? And the thickness T, which is 35 millimeter, clear? So I will write this area P divided by shearing area is 30 is this diameter, which is, you can see 30 millimeter. So in meter, it is 0.03, and pi D, clear? And thickness is 35 millimeter, which is 0.035, clear? And we know that allowable shearing stress is 170 megapascal. So 170 into 10 to the power 6 is equal to this P, which will cause shearing at A, divided by pi into 0.03 multiplied by 0.035. So from here, what you will get this P will be equal to 170 multiplied by 10 to the power 6 multiplied by pi multiplied by 0.03 multiplied by 0.035, clear? And when you calculate it, you will get P will be equal to 56100 000 Newton, and in kilonewton this P will be equal to 561 kilonewton. So this P is based on, is for A. This is A. You can see this is along A. This P is for along A. Now we will calculate this P force based on shearing stress along B. So you can see this is B, and here it may cause the shearing due to this load. These 2 points may shear. So you can see that this is also a cylindrical surface. So you can see this diameter is 58 millimeter. So pi into D, its diameter, multiplied by its thickness, which is 20 millimeter, will give you area. So I can write it, tau allowable is equal to P divided by A of B. So P divided by area of B. Shearing area will be equal to pi into D is 58 millimeter, which in meter is 0.058, and thickness is 20 millimeter. So 0.02 meter. And tau allowable is given as 170 megapascal. So 170 into 10 to the power 6 is equal to P divided by pi multiplied by 0.058 multiplied by 0.02, and you can get this P is 170 multiplied by 10 to the power 6 multiplied by pi into 0.058 multiplied by 0.02, and you will get this P will be equal to 620,000 Newton, or you can say that P is equal to 620 kilonewton. Now you can see this P along A, and this P is for along P. So what to choose is that our answer will, we will choose P is equal to 561 kilonewton as largest or maximum axial load. Why? Because you can see that this is smaller and this is greater, so it will be safer, clear? So what if I choose this one? So let me discuss it also. If you put P in this formula, tau allowable at A is equal to P divided by pi multiplied by 0.03 into 0.035. Clear? So you can see that P is 620 kilonewton into 10 to the power 3 divided by pi into 0.03 into 0.035. So you will get allowable at A will be equal to 187.94 megapascal. And you can see we have been given that allowable shearing stress is 170 megapascal. So it will cause the failure. So hence this value will be the safer, because if you put it in this formula, your allowable shearing stress at B will be less than allowable shearing stress. So hence we will select this value, and that is the answer of our this question. That was all about this problem 1-80. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-24 that is taken from chapter number 1, Stress, and book name is Mechanics of Material by RC Hibbeler. And the topic is internal loading. This is a complex problem. So statement is determine the resultant internal loading acting on the cross section of semicircular arc at C. So we have to find the internal loading at C, which means that we have to find the normal force, we have to find the shear force, and we have to find the moment. So I will write it. What we have to find is we have to find internal loading, which means the shear force, normal force, and moment. So let's start with the solution. So first step is that if I remove this pin support at point A, so there will be a reaction force in y direction, which is AY, and if you remove this, there will be horizontal reaction force. Similarly, there will be a vertical reaction force if we remove this roller support, so that will be equal to BY. So what we are going to find this BY, and then we will cut this arc beam over here, and we will take this area in order to find internal loading at point C, which is VM and N. Clear? So let's find it. Now what we will do, you can see that there is a angle theta is given, which is theta, and the radius arc is given, and there is a uniformly distributed load on this arc. Clear? So what we will do is that we will take a small differential area element. For example, that this is theta, so this angle will be equal to d theta. Clear? And this is the portion over which we are analyzing the force. So since this is distributed force, so when we convert this distributed force into a point force, so since this is differential force, so this differential force will be equal to this W naught times this arc length, which will be equal to r theta, because this is r and this is d theta, so it will be W naught r d theta. Clear? Now you can see that this force is acting perpendicular to it, so it is also making theta with the horizontal. Clear? And this will have two components, one along x direction, clear, and one along y direction. So we'll find these two components. So this is theta, so this component will be equal to W naught r d theta into cos of theta, and this component will be equal to W naught r d theta into sine of theta. And you can see distance from this to this is r. So again, if I draw a perpendicular line from this point, so you can see this distance is r. So this distance will become equal to r cos theta, because this is theta angle. So this is r cos of theta, and this remaining distance will be equal to r minus r cos of theta. So r minus r cos theta is actually, if you take r common, so it will be 1 minus cos of theta. Clear? Now we are ready to apply the equation of equilibrium. So first equation of equilibrium is that sum of all forces along sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, these two forces are not producing moment because they are passing through it. So first force which is producing moment about point A is By into perpendicular distance is 2r, because this distance is r and this is r, so it will be 2r. And this is producing counterclockwise moment, so it will be positive. So I will write By into 2. So y should be on the lower side, on lower right side, By into 2. Now the second moment will produce due to this horizontal component, which is this one, and the perpendicular distance is this one. And this distance, you can see this, since this is r, so and this is theta, so this component will be equal to r sine of theta. So this component multiplied by this component will give you the moment, and this will produce clockwise moment, so it will be negative. So I will write minus W naught r d theta into cos of theta multiplied by r sine theta. And you can see that this is differential force. So for taking the net force over entire curved beam, I will integrate it, so it will be integral of 0 to pi. Clear? And same is the case, the third force will be this df sine theta, which is W naught r d theta sine theta, and now perpendicular distance is this one, which is r into 1 minus cos theta, and it is also producing clockwise moment, so it will be negative. So I will write minus integral of 0 to pi W naught r d theta into sine theta multiplied by r into 1 minus cos of theta, and that is their sum of all moment about point A is equal to 0. So if you simplify it further, so By multiplied by 2, and that will be, you can see W naught into r, and r, these are constants, so we will take it out, so it will be equal to minus W naught r square and integral of 0 to pi cos theta into sine theta d theta. And same here, we will get W naught r into r is common, so W naught r square will be common, and we will left with 0 to pi, and it will be sine theta into 1 minus cos theta into d theta is equal to 0. Now further simplify it, By into 2 is equal to By into 2r, so you have to multiply it with r, By into 2r. So By into 2r minus W naught r square integral of 0 to pi sine theta into cos theta into d theta minus W naught r square, and we will have integral of 0 to pi sine theta into d theta minus integral of 0 to pi sine theta into cos theta d theta is equal to 0. Okay, so we will get By into 2r minus W naught r square into integral of 0 to pi sine of theta into cos of theta d theta minus this will be W naught r square integral of 0 to pi sine theta into d theta, and that will be plus W naught r square integral of 0 to pi sine theta into cos theta d theta is equal to 0. So you can see this will cancel with this, and we will left with by into 2r minus w naught r square integral of 0 to pi sine theta into d theta is equal to 0, and by into 2 minus w naught r square, clear, and that will give you integral of this sine theta will give you minus cos of theta from 0 to pi. So we will get, so this by into 2r minus w naught r square, and that will be minus cos of pi, minus minus will be plus cos of 0 degree is equal to 0. So by into 2r minus, this will w naught r square, and this is 2. You can calculate it, this is 2. So by into 2r minus 2 w naught r square is equal to 0. So from here you will get by is equal to w naught into r. Now you have this by, clear. So what we will go is that we will section this beam at this point, and we will concentrate on this portion. So I have already taken this section. So what we will do is that you can see you have by is this one, which is by is equal to w naught into r. So when you cut it, so you will be having a normal force at point C, like this is nc. You will be having a shear force which is equal to vc, clear, and you will be having a moment which will be equal to mc, and this is the origin or center point O. So we will find this mc, nc, and vc. What we will do is again that you can take the differential, that this is the theta. So we will take a differential element. This will be equal to d theta. So this differential element will be having a differential force which will be perpendicular to this there, and this df will be equal to w naught r into d theta. And again you can see the total angle is theta. So this will also make, it will have two components. One is this one, another one is this one. So this component will be equal to w naught r d theta into cos of theta, and this will be equal to w naught r d theta into sine of theta. Okay, now we'll apply equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see one force which is nc is in positive direction, and the other component of this force in this negative direction. There is no other horizontal force here. Sum must be equal to 0. So I can write nc minus w naught r cos of theta into d theta. Since this is differential equation, so if I integrate from 0 to pi, clear, from 0 to pi by 2, sorry, pi by 2, so we will get a net force, horizontal force acting on the system. So I will integrate it from 0 to pi by 2. Okay, is equal to 0. So from here nc will be equal to integral of w naught r cos of theta into d theta, and 0 to pi by 2. It will be equal to w naught r integral of 0 to pi by 2 and cos theta into d theta. So when you calculate it, you will get 1 from this integral of pi by 2, integral of cos theta into d theta pi by 2, and you will get nc will be equal to w naught into r. Clear? Now we'll find this vc by using another equation of equilibrium, and that is sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see one force upward is w naught into r, the second force is vc, and the third force is this downward force. So minus w naught r sine of theta into d theta. And since this is differential force, so for entire length from 0 to pi by 2, we will get, if we integrate this force, we will get a net vertical force. So I will write integral of 0 to pi by 2 is equal to 0. Now w naught into r plus vc, and this is minus w naught r integral of 0 to pi by 2 sine of theta into d theta is equal to 0. And you will get 1 from this as well. So you will get w naught into r plus vc minus w naught into r is equal to 0. So from here vc is equal to 0. It means that there is no shear force at point C. And the last thing is that we will find this moment nc. So what we will do is that we will apply equation that sum of all moment about point A is equal to 0, taking the counterclockwise moment as positive. Since this force is passing through point A, it is not producing moment, clear, and this force, net force, is also passing through point A, it is not producing moment. So only moment is produced by this by into perpendicular distance is r, and nc into perpendicular distance is r. So I will write nc into r, this is producing clockwise, clear, nc into r, this is clockwise, plus this by into perpendicular distance is r, and this is counterclockwise, so it will be plus. So by, which is w naught into r, and perpendicular distance is r, plus this mc, which minus mc, which is clockwise, minus mc. Their sum must be equal to 0. So nc is w naught into r, so it will be minus w naught r square, plus this will be w naught r square minus mc is equal to 0. So it means that moment at point C will be also equal to 0. So you can see we have found internal loading nc, vc, and mc at point C. Clear? And that was all about this a little bit complex problem 1-24. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching me and supporting me. Welcome back. In this video, we are going to solve problem 6-152 that is taken from chapter number 6, Bending, and book name is Mechanics of Material by RC Hibbeler. And the topic is stress concentration. So statement is the bar is subjected to a moment of 40 Newton into meter. Determine the smallest radius r of the fillet so that allowable bending stress is 124 megapascal is not exceeded. So you can see this bar is exerted by a moment that is 40 Newton into meter. The cross section here is shown as this height is 80 and the width is 7 millimeter. And here the height is 20 millimeter and the width is 7 millimeter. Clear? So due to change in cross section area from 80 to r to 20, there is stress concentration in this region. So we have been given allowable bending stress is this. So you have to determine the smallest radius r of this fillet. Clear? So let's start with the solution. As we know that allowable bending stress for this stress concentration will be equal to K into MC divided by I. So what will be the M? M is moment, clear? So moment will be equal to 40 Newton into meter. What is C? So you can see that the stress concentration will be maximum in this region. So we will take the cross-sectional area of this portion. So the cross-section area will here will be, you can see this height is 20 millimeter. So we will take this as 20 millimeter and thickness is 7 millimeter. it's 7 millimeter. So if you take the half of this, that will be its neutral axis here, and C is distance from neutral axis till topmost. So it will be equal to C, and this C is equal to 20 divided by 2, which is equal to 10 millimeter. So I will write C is equal to 10 millimeter. So we will convert into meter, and that will be equal to 0.01 meter. Now I for I is the second moment of inertia for this rectangular section, which is equal to 1 over 12 BHQ. Clear? So put the value 1 over 12. B, which is breadth, is 7 millimeter. In meter it is 0.007. Clear? And height is 20 millimeter. So in meter it is 0.02 Q. So when you calculate it, you will get the second moment of inertia for this rectangular cross sections will be equal to 1 over 12, 0.007, 0.02 whole cube. You can calculate it. So this will be the I. Now what we will do is that we have been given the allowable bending stress, which is 124 megapascal. So we know that allowable bending stress is equal to K M into C divided by I, where K is stress concentration factor. So sigma allowable is 124 megapascal. So 124 into 10 to the power 6 is equal to K. And what about MM is 40 Newton into meter. So 40 multiplied by C is distance, which is 0.01 divided by this I, and I is 1 over 12, 0.007 into 0.02 whole cube. So from here you will get this K, and this K will be equal to 124 multiplied by 10 to the power 6 multiplied by 1 over 12 into 0.007 into 0.02 whole cube, and you will divide it by 40 multiplied by 0.01. So from here when you calculate it, you will get K will be equal to 1.45. So I will write K is equal to 1.45. Now you will use this table, so you can see that this case is similar to this. So what we are going to find is we have K value clear, and we will find W by 4H. So here this is W, which is, you can see the maximum height, which is W, and this is 80 millimeter, and here the height is 20 millimeter. So what we'll write is that W is equal to 80 millimeter and H is equal to 20 millimeter. So we are going to find W by H ratio. Clear? So W divided by H, so W is 80 and H is 20, so you will get 4. Clear? So W by H is 4. Now what we will do is that you can see K is 1.45, K is 1.45, and W by H is 4. So you can use this table. So from here what we will get is that if I draw, this is K on y-axis, this is K, and this point is 1.45. So this line is 1.45. Clear? And what about W by H is 4? So you can see this is the figure. So this point is the point. And if you draw the vertical line from here, so you can see this point is 0.25, and this 0.25 is R by H. So we will get R by H is 0.225. Okay. So I will write from table or from figure 6-43 with K is equal to 1.45 and W by H is equal to 4. We get R by H is equal to 0.25. So from here R will be equal to 0.25 times H. Since H is equal to 20 millimeter, so put it, R will be equal to 0.25 times 20 millimeter, and you will get R will be equal to 5 millimeter, which is the radius of this fillet, and is the answer of this question. So this was all about this problem 6-152. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-88. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by RC Hibbeler. So statement is, if the beam has a square cross section of 9 inch on each side, determine the absolute maximum bending stress in the beam. So you can see this is a cantilever beam, that is, and A is fixed, and from A till a length of 8 feet we have uniformly distributed load, and at point B we have a point, a concentrated load of 1200 pounds. And the cross section is that this is a square cross section 9 inch by 9 inch. So you have to determine the absolute maximum bending stress in the beam. So let's start with the solution. So first step is that if you remove this fixed support at point A, so you will be having a reaction force which is represented RA, and you will be having a moment which will be MA. So we'll find this RA and MA by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So you can see this is counterclockwise moment, so it will be positive. So I will write MA. The second moment will be due to this load, which is 1200, and now perpendicular distance is 16 feet. Clear? And this is producing clockwise, so it will be negative. So I will write minus 1200 into 16. The third load is due to this uniformly distributed load, so we will convert this uniformly distributed load into a point load, and that will act at the middle of this 8 feet. So this distance will be 4 feet, and this remaining will be also 4 feet. Now this distributed load when converted into point load, so it will be equal to 800 over the length, entire length over which it acts. So this will be equal to 6400 pounds. Now due to this load about point A, the perpendicular distance is 4 feet, and it is also producing clockwise, so it will be negative. So I will write minus 6400 multiplied by 4 is equal to 0. So from here you will get MA will be equal to this 1200 into 16 will give you 19,200, plus this 6400 into 4 will give you 25,600. So when you add them, you will get moment about A comes out to be 44800 pounds into feet. So this will be the moment. Clear? Now we will find this RA by using equation of equilibrium. The second one, which is sum of all forces along y direction, must be equal to 0, and upward force is taken as positive. So you can see RA is upward, minus this 6400 is downward, minus 1200 is downward, and their sum must be equal to 0. So I will write RA minus 6400 minus 1200 is equal to 0. So from here you will get this RA will be equal to 7,600 pounds. Now you have RA and RMA. So what we are going to do is that we will draw the shear force and bending moment diagram, and from there we will take the maximum bending moment. So what we will do is that we will take vertical line from the end of this beam, and similarly vertical line from the other end of the beam, and then there is a horizontal line to show the length in feet. So X will be in feet. On y-axis you will take the shear force that will be in pounds. Okay, let one division is 2000. So 2000, this is 4000, this is 6000, this will be 8000. Okay, now at point A we have RA, which is equal to 7600. So what we will do is that we will plot 7600. Let 7600 is this point. Okay, now if you take a vertical line from this, so this length will be 8 feet, and this distance will be, the other one will be also 8 feet. Clear? Okay. Now we want to find the shear force at this point. So you can see the shear. This is the load which is 800 over the length which it at is 8. So it is 6400. So what we will do is that this is downward force. So this force will be minus 6400. So 7600 is there. Minus 6400 will cause it to 1200 plus 1200. So over here we will have plus 1200. So let plus 1200 is this point. This is 1200. Now you can see that this load is straight line, clear, is of 0 degrees. So shear force will be 1 degree higher, and it will be a straight linear line, and slope will be decreasing because this load is downward. Now moving from this point till end, there is no other shear force, so it will remain horizontal till end. And at the end, you can see you have minus 1200. So plus 1200 minus 1200 will bring it to 0. So it will come down. So this is your shear force diagram. Now we draw the bending moment diagram. So for bending moment diagram, I will take a horizontal line to show X in feet, and on y-axis we will have movement having unit pounds into feet. Okay, let one division, you can see the movement is in 10,000. So we will take one division is 10,000. So downward is minus 10,000, minus 20,000, minus 30,000. Similarly, this will be minus 50,000. Now at point A, you can see you have a moment of MA, which is 44,800 pound into feet. So this is counterclockwise. While drawing it on bending moment diagram, this counterclockwise movement will cause it to toward downward. So we will locate it as minus 44,800. So let this point is minus 44,800 pounds into feet. Now area under the shear force diagram will give you the bending moment. So this area, you can see this is trapezoid. This length is 7,600 and this height is 1,200. So how we'll find this area? Let this area is A1. So A1 will be equal to this height, which is 7,600 plus this height. So I will write it 7,600 plus 1,200 divide by 2 into this breadth, which is equal to this breadth, which is equal to 8 feet. This is how we find the area of trapezoid. Okay, so when you solve this area will be equal to 35,200. Now here the moment is minus 4,480 minus 4,480 plus this 3,5,200 will cause it to change it to minus 9,600. So at this length we will have minus 9,600. So let this point is minus 9,600 pounds into feet. Now you can see that this shear force is a 1 degree line and slope is decreasing. So bending moment will be a second degree curve and it will be in clockwise direction. So I will join these 2 points by using this curve here. Now the second area under the shear force diagram is this area. Let this area is A2. So you can see A2 is equal to this height. This is rectangle. So this height multiplied by this width. So 1,200 multiplied by 8. So 1,200 multiplied by 8 will be equal to 9,600. So minus 9,600 plus 9,600 will be equal to 0. So bending moment will be 0 at this point. So our new point will be this one. Clear? Now you can see that shear force is a horizontal line with 0 degree and this is positive area. So bending moment will be 1 degree higher. It will be a linear line and slope will be increasing. So we will join these 2 points using straight line. So this is your bending moment diagram for this beam. Now from BMD bending moment diagram, we can see that maximum absolute value of bending moment is equal to, you can see one is this one, the other one is this one, and third one is 0. So this is the maximum value. So minus 44800, and unit will be pounds into feet. So this maximum bending moment absolute value will be equal to 44800 pounds into feet. Now if you want to convert it into kips, so 44.8, it will be kilopounds, which is equal to kips into feet. Okay. Now, if you want to convert this feet into inch, so what we will do is that 44.8 multiplied by 12, and the unit will be equal to kips into inch, because 1 feet is equal to 12 inch. So this is the maximum bending moment. And we know that maximum bending absolute value of bending stress is equal to maximum bending moment into C divided by I. Since we have been given a square cross section of 9 by 9, this is 9 inch, and this height is also 9 inch. So we will find the moment of inertia for this beam, and if we take the half of this will be its neutral axis, NA, and for this I is equal to, I for rectangular or square is 1 over 12 BH cube. So here B is 9 and H is also 9, so 9 power 3, that will give you I. And when you calculate this I will be equal to 546.75 inch power 4. What about C? So C is distance from neutral axis till top or bottom, so this are C, which is equal to 9 divided by 2. So C is equal to 9 divided by 2, which is equal to 4.5 inch. Clear? Now you have all the values. You can just put it in this formula. Maximum absolute value of bending stress is equal to moment, which is equal to 44.8 multiplied by 12. Unit is kips into inch divided by I, which is having 546.75 inch power 4, and C is 4.5 inch. So we will left with we will get 4.42 kips, which is kilopound, clear, divided by inch square. And that is maximum absolute value of bending stress. And when you calculate it, this is maximum absolute value of bending stress is 4.42, and kips per square inch will be equal to KSI, which is kilo pound per square inch. And that is the answer of our this question, in which we have calculated the maximum absolute bending stress for the beam and loading shown. I hope you have enjoyed this video. If you are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-150. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by RC Hibbeler. And the topic which we are covering is stress concentration. The statement of problem is the bar is subjected to a moment of 153 Newton into meter. Determine the smallest radius R of the fillet so that allowable bending stress is 120 megapascal is not exceeded. So you can see this is the bar where there is a moment of 153 Newton into meter. Now you can see this is not a uniform bar. Here this height is 60 millimeter and here the height is 40 millimeter, and there is a fillet of radius R. So due to this fillet radius, there is an abrupt change in the dimension of this rod. So there will be a stress concentration. So stress concentration is the point in the part which is this one. So here where the stress is significantly higher than the surrounding area. So we will use this formula: sigma max is equal to K into MC over I. What is K? K is stress concentration factor, which will be taken from this table. So you can see this is the book. This table is available here. Figure 6-43 and 44. So we will use this. So let's start with the solution. So what will be the first step is that we will write the formula, which is sigma max is equal to K into MC divided by I. Clear? So we'll find K for this. We have sigma max or allowable stress. This is also allowable is the maximum stress. So maximum stress is given, which is 120 megapascal. So 120 into 10 to the power 6 pascal is equal to K, which is not known. The moment is given as 153 Newton into meter. And what about C? So C is distance from neutral axis or neutral axis. This is the axis. Clear? So this cross section is total height is 40 millimeter. Clear? This is 40. So this distance will be equal to C, which is equal to 20 millimeter. And if you have the cross section of this smallest section, let me draw it. So it will be like this. This is your total 40 millimeter. Clear? And this width is 7 millimeter. The width is 7 millimeter. So this will be its neutral axis, and C is distance from neutral axis till top or bottom. So this is 20 millimeter. The question is that why we are taking this region instead of this, because we have already discussed that stress concentration occur at this point. So here this is the smallest height, so we will counter this in order to calculate the maximum stress. So I will get C is equal to 20 millimeter, which in term of meter is 0.02 meter. And what about I for this cross section? So I is 1/12 BH cube. So B breadth is 7 millimeter, which is 0.007, and height is 0.04 power 3. Okay, 0.04 power 3. So when you calculate it, you will get the value of K, which will be equal to 1.46. Now you have this value, so you can see that there is a fillet in this side. So we will use this case, and again from here we will calculate something. Here you can see W, H, T, and R. So we'll first calculate W by H. So W by H for this. So here W is this one. This is your W, which is equal to 60 millimeter, and that is 0.06 meter. Or you can also take 60. And this is your H. And because H is for the lower portion, you can see this is H and this is W. So I will write W is 60 and H is 40, which will give you 1.5. Now what we will do is that for W over H is equal to 1.5. This is the graph. You can see this middle portion here, and K is 1.5. So K is 1.5, and this is W by H is this W by H is 3. So this will be the portion. So if you go toward downward, so this will be 0.2. So what we will do is that from figure 6-43, you will get this value 0.2. I will also repeat it. You can see that this is 1.5, and this, when you come down, it will be 0.2, which is R by H. Here, this is the line graph of W over H is equal to 1.5. So what we will get is that we will get 0.2 is equal to this small R by H. Here, now from here, this R fillet, R represent this fillet. So this R is equal to 0.2 times H. So H is 40 millimeter. So multiplied by 40 will be equal to 40 millimeter. So this radius R fillet will be equal to 8 millimeter, which is the answer of this question. So for allowable bending stress of 120 megapascal, we will have this fillet radius will be equal to 8 millimeter, and it will not exceed the 120 megapascal. And that was all about this problem 6-150. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-189. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by RC Hibbeler. So statement is determine the maximum bending stress in the handle of cable cutter at section AA. A force of 45 pounds is applied to the handle. The cross section area shown in the figure. So you can see this is the cable cutter, and this handle is acted upon by a load of 45 pounds. So what we have to find? We have to find the maximum bending stress in section AA of cutter cable. So let's start with the solution. So when you cut this handle of the cutter cable at section AA and draw the free body diagram. So let me draw the first the free body diagram of this cable handle. So this is the cable handle. Let me draw it first. So here you can see you have a load of 45 pounds that will be acting downward. This is 45 pounds. The length of this load and this line, vertical line, is this length is given as 5 inch, clear, and from this till this angle is 20 degree. You can see from the figure this is 20 degree, and from here till where you cut the handle, this distance is given as 4 inch. Yeah. So when you cut it over a length of 4 inch, so you will be having a shear force on this face which will be acting upward. This is V force. You will be having a normal force perpendicular to this face which is equal to M, and as well as you will be having a reaction moment which is like this. So you will find this moment for finding the bending stress. We can also find V and M, but we will here find this M because we will find this M because we will have maximum bending stress is equal to moment into C divided by I. So how we'll find this M? So what we will do is that this is section AA, you can see point 1. So we'll find this by using equation of equilibrium, that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So one moment which is external about this point 1 is this moment M, so I will write plus M. Clear. The second moment will be due to this load 45, and perpendicular distance between this and this is this distance. Clear. So this is 5 inch and this is hypotenuse which is 4 inch. So we'll find this distance as well, and this distance is 40 cos of 20 degree. So how we'll find this? So you can see that let me draw it like this. This distance, this angle is 20 degree. How? Let me explain. You can see this line is perpendicular to this horizontal line, and this line is perpendicular to this surface. Clear. So the angle between these two lines will be also equal to 20 degree. And this distance, you can see this is hypotenuse which is 4. So this is the base. So if you take cos of 20 degree, so cos of 20 degree is equal to, let this is x divided by 4. So x will be equal to 4 cos of 20 degree. So this distance is 4 cos of 20 degree. And this remaining, this distance is 5 inch. So total distance will be equal to 4 cos of 20 plus 5, and this is perpendicular distance for this 45, and the moment will be clockwise, so it will be negative. So I will write minus 45 into 5 plus 4 cos of 20 degree is equal to 0. So when you calculate it, you will get this moment will be equal to 394.14 unit will be pound into inch. Now you have this moment, so you can use the equation which is maximum bending stress is equal to maximum moment into C divided by I. The cross-sectional area is given as rectangular height is 0.75 and width is 0.50. So if I draw it like this is the rectangular section. This distance is 0.5 inch and the height is 0.75 inch. Clear? So if I divide it in between or half of 0.75, so it will be its neutral axis, and this distance will be equal to 0.75 divided by 2, which is equal to 0.375. And what is C? So C is distance from neutral axis till the outer surface, either this or this. So both are equal. So C will be equal to 0.375 inch. So I will write C is equal to 0.375 inch. And I, moment of inertia for rectangular beam or rectangular cross section, is equal to 1/12 PHQ. So here 1/12, B is 0.5 and H is 0.75 whole cube. Now you have I, you have C, and you have M. You can just put in this formula. Maximum bending stress is equal to moment, which is 394.14 into C is 0.375 divided by I is 1/12, 0.5 into 0.375 whole power cube. So when you solve this, you will get maximum bending stress comes out to be 8.41 into 10 to the power 3 pound per square inch PSI. So in terms of KSI, you can write maximum bending stress is equal to 8.41 KSI. And that is the answer of this question, that at section AA, the maximum bending stress will be 8.4 KSI. And this was all about problem 86-189. I hope you have enjoyed this video. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. Problem 6-191. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Materials by RC Hibbeler. Statement is determine the shear and moment in the beam as a function of x, where x is greater than 0 and less than 6 feet. Draw the shear and moment diagram for the beam. So you can see this is a cantilever beam here, where there is a point load at this end which is 8 kips. At a length of 4 feet, we have clockwise moment of 50 kips into feet, and there is a distributed load from fixed end till the length of 6 feet, and the magnitude is 2 kips per feet. So we have to determine the shear and moment equation in terms of x for the region x is greater than 0 and less than 6 feet, and then we will draw the shear force and bending moment diagram. So let's start with the solution. If we remove this fixed support at this end, so we'll be having a reaction force. Let this is your point number 1. So there will be reaction force which is R1, and there will be a moment as well. Clear? So this we will find this R1 and M1 by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So about this point 1, one moment will be due to this 8 kips load, and the perpendicular distance is this 10 feet, and this is producing clockwise moment, so it will be negative. So I will write minus 8 into 10. The second moment is this one, which is 50 kips per feet into feet, and this is again clockwise, so it will be also negative. So minus 50. Now you can see you have a distributed load, so we will convert this distributed load into a point load. So for that, we will multiply this 2 kips per feet with the length over which it acts. So 2 into 6, which is 12, and this load is acting downward, and that will be acting at a half of the total length. The total length is 6 feet over which this distribution load acts, and the half will be 3 feet. Okay, so the third moment will be due to this 12 kips load, and perpendicular distance is 3, and this is also producing clockwise moment, so it will be negative. So I will write minus 12 into 3. And the last moment is this reaction moment, which is counterclockwise M1, and that will be positive, but the sum of all moment about point 1 must be equal to 0. So from here we will get M1 minus 80 minus 50 minus 36 is equal to 0, and we will get this M1 will be equal to 166 kips into feet. So this is the reaction moment when you remove this fixed support. Now we'll find this R1 by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So R1 is upward, 12 is downward, that will be minus, and minus 8 will be, their sum must be equal to 0. So R1 minus 12 minus 8 is equal to 0. So it means that R1 is equal to 20 kips. Now you have R1 and moment M1. So what we will do is that we will section this beam in the range of x is greater than or equal to 0 and less than 6 feet and draw the free body diagram. So if I draw it over here, that this is the beam, this is point 1 where we have a reaction force R1. R1 is 20 kips and the moment was, we calculated, is 166 kips into feet, that is counterclockwise. And this length which we have cut the beam is x, and there is a distributed load over a length of x, and this distributed load is downward. So when you convert this distributed load into point load, so it will be acting at the mid, clear? And the magnitude of this distributed load is 2 kips per feet. So this point load will be equal to 2 into x. And that will act at the half of the x. So this will be equal to x by 2, and the remaining will be also x by 2. And when you cut the beam, you will be having a shear force that will be, you will take it downward, V, and you will be having a reaction moment, M. So we'll find this V and M in terms of x. How we'll find this? So by using equation of, this is point O. So we'll find this M and V by using equation of equilibrium. The equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So 20 is upward, minus 2x is downward, and minus V, their sum must be equal to 0. So 20 minus 2x minus V is equal to 0. So from here we will get V is equal to 20 minus 2x, and the unit will be in kips. This is your shear force. Let this is equation number 1, which is the equation of shear in terms of x, and this is for region x is greater than or equal to 0 and less than 6 feet, where we have cut the beam. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point O is equal to 0 and taking the counterclockwise moment as positive. So about this point O, the first moment will be due to this 2x and perpendicular distance is x by 2, and this is producing clockwise moment, so it will be positive. So I will write 2x into perpendicular distance is x by 2. The second moment will be due to this 20 kips load and perpendicular distance is x, and this is producing clockwise, so it will be negative. So I will write minus 20 into x. The third moment is this 166, that is clockwise, counterclockwise movement, so it will be plus. So I will write plus 166, and the last movement is external movement, which is considered as counterclockwise, so it will be also positive, and their sum must be equal to 0. So from here you will get m plus x square, because 2x into x by 2 will be x square, minus 20x plus 166 is equal to 0. So this movement equation will be equal to minus x square plus 20x and minus 116, and the unit will be kips into feet. And this is equation number 2. So equation number 1 and 2 are shear force and bending moment equations in term of x, and here you will use x is greater than 0 and less than 6 feet. Clear? So this is the answer of our first part. Now we'll move toward drawing the shear force and bending moment diagram. So for what we will do is that we will take the vertical line from the end of this beam, and first we will draw the shear force. So for shear force I will take a horizontal line to show length x in feet, and on y-axis we have shear force and unit will be kip. Clear? So what, that one division is equal to 5. So 5 plus 10 plus 15 and plus 20, and similarly downward that is minus. Okay, so for region of, if I draw a table, clear, and the table will be like that, x value shear force in kips and moment will be kip into feet. So for x is equal to 0, you can put it in this equation number 1. So when you put x is equal to 0, this v will be equal to 20. So I will write v will be equal to 20 kips. And for x is equal to 0, so this will be 0, this will be 0, and moment will be minus 166. So I will write minus 166. Similarly, for region of x is 6 feet. So if you put x is equal to 6 feet, so it will be minus 12. So 20 minus 12 will be equal to 8 plus 8. So v will be plus 8. Similarly, you put x is equal to 6 feet in this equation, and you will get moment will be equal to minus 82. Okay. So for x is equal to 0, we have v is equal to 20. So what we will do is that for x is equal to 0, our first point is this one. Clear? And for x is equal to 6 feet, so this is 6 feet length. We have shear force is 8 plus 8. So we will locate plus 8. So plus 8 will be somewhere here. Let me choose the point. This will be plus 8. Now you can see that shear, this loading is a uniformly distributed load, a load with a horizontal line and half 0 degree. So shear force will be 1 degree higher as the load is downward. So it will be a linear, the shear force will be a linear line, and slope will be decreasing. So we'll join these 2 points using straight line. So this will be the loading. Now moving from this point till this point, we do not have any other force, so shear force will remain horizontal. So it will remain horizontal till the end, and at the end you can see you have minus 8 downwards, so that will cause it toward downward 0. Clear? So this will be your shear force diagram. Now we'll draw the bending moment diagram. So for bending moment diagram, I take a horizontal line to show the length x in feet, and on y-axis we will having moment that will be unit kips into feet. Let one division is of 100, so minus 100, minus 150, and minus 200. So for x is equal to 0, we have moment is equal to minus 166. So minus 166, let minus 166 is this point. This is minus 166. And for x is equal to 6, we have moment is minus 82. So let minus 82 is this point. Minus 82 is this one. Minus 82 kips into feet. Now you can see that shear force is a linear line with slope decreasing, so bending moment will be second degree curve and it will be in clockwise, rotation will be in clockwise direction. So we'll join these 2 points by using a curve. Okay. At this point, you can see you have external movement of 50 kips into feet, that is clockwise. So while drawing in bending moment diagram, it will cause the bending moment to go upward. This is convention given in the book. So minus 82 plus 50 will equal to minus 32. So bending moment will change to minus 32. So let this point is minus 32. So your bending moment will change toward this. Okay. And the last one is this area under the shear force diagram, and you can see this area is, this height is 8 multiplied by length is 4. So 8 fours are 32. So minus 32 plus 32 will be equal to 0 at this point. So you will get the shear bending moment 0 at this point. And we will join these 2 points using a straight line here, and that will be your bending moment diagram, and which is the answer of our second part. So that was all about problem 6-191, in which first we solved the shear force and bending moment equation in terms of x, and then we draw the shear force diagram and bending moment diagram. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-194. This problem is taken from chapter number 6, bending, and book name is Mechanics of Material by RC Hibbeler. So statement is the strut has a square cross section A by A and is subjected to bending moment applied at angle theta as shown. Determine the maximum bending stress in terms of A, M, and theta. What will be the angle theta will give you the largest bending stress in stress? Specify the co-orientation of neutral axis for this case. So this is a square strut having side A by A and is applied with a moment here at angle theta from the Z axis. So you have to find the maximum bending stress in terms of A, M, and theta. You have to find theta for the larger bending stress, and you have to determine the neutral axis for this case. So let's start with the solution. So you can see that this moment is applied at angle theta from this axis. So it will have, if we resolve it into 2 components, so the first component will be this one, and this component will be, this will be like this. This component will be equal to m cos theta, and that will be minus because it is opposite to z. And similarly, it will having a vertical component like this. So this will be equal to, again, this will be minus m sine of theta because it is opposite to y. Clear? And this will be in this direction. So if I write it over here, so this will be the vertical component will be like this. Okay. So vertical component will be like this, minus m sine theta. Now let this is your point A. We will specify these 2 points, and this is point B. So you can see this is z axis and this is y axis. So this is moment about z. So I will write it is equal to mz, and this is moment about y axis. Clear? So it is moment about y. So due to moment about z, clear, this is like this. This will be like this, causing this surface to bend like this. Then the upper portion, this point A, will be in tension, and due to this movement about y, it will also cause it to bend like this. So you can see point A is in point A is the position where we'll have maximum bending stress. So we will find this bending stress. So we will write this mz is equal to minus m cos of theta, and this my will be equal to minus m sine of theta. We will find section properties, which is the second moment of inertia for this strut, and this moment, second moment of inertia, I about y axis is equal to I about z, because this is square strut. So we have 1 over 4, 1 over 12 bh cube. So b is a and h is also a. So 1 over 12 a power 4. So this is 1 over 12 a power 4. Now for maximum bending stress, I will write the formula. Maximum bending stress, as I have already discussed, that maximum bending stress will be at point A. So it will be at point A. So what is the formula for? Now the stress that will be due to this movement about z axis and due to movement about y axis will be a combination of both this. So I will write stress is equal to, first, due to movement about z. So I will write minus m into z multiplied by y divided by I double z or iz, and minus m into y into z divided by I y. Why? You can see for this case, this is movement about z axis. Clear? So this vertical distance, we know that the stress due to this will be equal to movement into y into distance. So this distance is in y direction. That is why we have taken this I, and I is about z axis. Similarly for this, you can see that this is the movement my, and this distance is in around z direction. So I about this y axis. Clear? So that is why this formula. Now we'll expand this. So we will write minus mz is minus m cos theta. So minus m cos of theta. What is y? Since point A is in positive direction of y, so it will be equal to, this total distance is a. Clear? So this will be equal to a by 2. So I will write a by 2 divided by iz is 1 over 12 a power 4, minus this moment about y is m minus m sine theta. So I will write minus m sine theta into this distance, which is also again a by 2 from this y axis, Okay, so I will write into a by 2 divided by 1 over 12 a power 4. So again, when you solve this, you will get sigma is equal to 6m over a cube into cos of theta plus sine of theta, which is the maximum bending stress in terms of a, m, and theta. So this is the answer of our first part. Now we'll find the second part, in which we have been asked to find the theta for the largest. So if we take the derivative of d sigma over dt and make it to 0, so you will get the angle. So let's take d sigma over d theta in equation 1, our answer of 1. So you will get d sigma over d theta will be equal to 6m over a cube into d over d theta into cos theta plus sine theta. So from here you can see that this d theta, d sigma over d theta should be equal to 0. So 0 is equal to 6m over a cube, and derivative of cos theta is minus sine theta clear. D cos theta, derivative of cos theta minus sin theta plus derivative of sin theta is cos theta. And from here you will get cos of theta minus sin of theta is equal to 0. Clear? And theta will be equal to 45 degree. Why? Because cos theta is equal to sin theta. So if I divide sin on both sides, so cos on both sides, so you will get 1 is equal to sin theta divided by cos theta. So we will get sin theta over cos is equal to tangent of theta is equal to 1. So if you take theta is equal to tangent inverse of 1, so you will get 45 degree, which is the answer of our second part. And in last part, we have to define the orientation of neutral axis. So for that, we have formula that tangent of alpha is equal to Iz over Iy into tangent of theta. Since Iz and Iy is 1 over 12 a power 4 into divided by 1 over 12 a power 4 and tangent of 45 degree. So this will cut with this and we will left with tangent of alpha is equal to tangent of 45 degree. So alpha is equal to 45 degree, which is the orientation of neutral axis for this case. So if I draw the orientation of neutral axis, so it will be like this. At 45 degree, you will take the orientation. So this is alpha, which is equal to 45 degree. And that was all about this problem 6-194. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-192 that is taken from chapter number 6, bending, and book name is Mechanics of Material by RC Hibbeler. So statement is a wooden beam has a square cross section as shown. Determine which orientation of the beam provides the greatest strength at resisting the moment M. What is the difference in resulting maximum stress in both cases? So you can see this is the square cross section having length A by A, and this is also a square cross section A by A. But the orientation here is this and the orientation here is like this, and they are both applied by same moment M and M. So you have to determine the orientation which provide greatest strength, and then you have to find the difference in resulting maximum stress in both cases. So let's start with the solution. So for case A, we know that maximum bending stress is equal to moment into C divided by I. So you can see here, this is moment M applied. So due to this moment, it will bend like this, clear. So this lower portion will be in tension and upper portion will be in compression. And this is the horizontal axis, because this horizontal axis is, this will be A by 2 and this will be also A by 2. So it will be symmetrical, A by 2. So here the maximum stress will be here, and this distance C will be equal to A by 2. So maximum stress is equal to M into C divided by I. So C is equal to A divided by 2 if you take this horizontal axis. So C is the maximum distance from neutral axis till outer surface. So this is C and this is equal to A by 2. What is the moment of inertia for this square? So it will be equal to 1 over 12. B is A, breadth is A, and height is also A. So 1 over 12 B H cube. So A cube. So I is equal to 1 over 12 A power 4. The moment of inertia formula for square is equal to, for square section is 1 over 12 B multiplied by H cube. So B here is A and H is also equal to A. So this is the moment of inertia. So put all these values in this formula. So maximum bending stress for case A is equal to moment, C is equal to A divided by 2, and I is 1 over 12 A power 4. So when you calculate it, you will get maximum bending stress comes out to be 6M divided by A power 3. So this is the maximum bending stress for case A. Now we'll move toward case B. So for case B, we have same formula. Maximum bending stress is equal to moment into C divided by I. Now you can see if I draw horizontal line, clear. So it will form two triangles. I take horizontal line from here, it will be two triangles, clear. So this side is A, this is also A, clear. So this distance by using Pythagoras theorem, that this is point A and this is point B. So AB will using Pythagoras theorem, AB square is equal to A square plus A square, which is equal to 2A square. So AB will be equal to under root 2A square, which will give you under root 2 times A. And this AB will be equal to 1.41 times A, clear. If I draw a vertical line from this top, this line, and this is point O, so and this is point C, so CO is perpendicular, so CO will be equal to, again you can see this is also same over AB, so it will be equal to AB, this distance will be equal to CO will be equal to AB divided by 2. So CO is equal to AB divided by 2, which is equal to 0.707 times A, clear. Now CO, from here C is the maximum distance from neutral axis till the topmost or bottommost. This is equal to C, this is also equal to C. So bending stress will be maximum over this because this point is in tension. So C is equal to 0.707 times A. Now moment of inertia I for this rectangular portion, since there are two rectangles, so the moment of inertia is 1 over 36 BH cube, and this area by using parallel axis theorem, its centroid will be away from this neutral axis, clear. So we will write AD square. So I will write 2 multiplied by 1 over 36 BH cube plus AD square, clear. So what is B here? So B is this AB. B is equal to this AB, which is equal to 1.41 times A. What is height? Height is equal to CO, and that is equal to 0.707 times A, clear. And what is area? So area will be equal to, for this triangle, is equal to 1 over 2 breadth into height. So 1 over 2, not 1 over 12. So this is 1 over 2 B into H. So B is 1.41 times A and H is 0.707 times A. And D is distance from neutral axis till the mid of this section, till the centroidal of this section. And for this triangle, its centroid will be equal to 1 over 3 of CO. CO is this distance. So 1 over 3, its C will be, I will choose another color, its C will be this one, and this distance is equal to 1 over 3 times CO. So 1 over 3 times 0.707 times E. Now you have all the values. This D, this is equal to D. So D is equal to 1 over 3 times CO, and that is 1 over 3 times 0.707 E. Now you have all the values. You can just put it in this formula. Clear? So you will get I. So I will write I is equal to 2 times. Why 2 times? Because we have two triangle. One is this one, another one is this one. So 2 times 1 over 36. Clear? B breadth base is this one AB, which is 1.41 times A, and height is CO, which is 0.707 A power 3, plus 1 over 2, which is the A, plus A. A is equal to 1 over 2. This is A. We have calculated 1 over 2 into 1.41 A into height is 0.707 times A into D square. So D is 1 over 3 into 0.707 A square, whole square. So when you calculate this I, so this I will be equal to 0.0833 A power 4. Now you have C, you have I, so you can put it in this formula. So you will get maximum bending stress will be equal to M into C divided by I. So M, C is 0.707 times A divided by I is 0.0833 A power 4. So when you calculate it, you will get the maximum bending stress comes out to be A power, 8.4853 times M divided by A cube. So this is the maximum bending stress for case B. Now you can see you have, this is for case A, and this is 6M, and this is for case B. So for applying the same moment over these two different orientation, this gives 6M, bending stress comes out to be 6M over A cube, while this give you bending stress is 8.4853 M over A cube. Since this value is smallest stress, so it means that the same moment is producing smallest strength as compared to here. Clear? So the safest or highest strength will be the case A. Clear? So I will write it over here. So case A provides higher strength since the resulting maximum stress is less for a given moment and A. Clear? You have seen that both have same M and both have same M A. So this is giving you the maximum bending stress here is less than maximum bending stress over here. Clear? So it means that this is producing maximum strength too, or it is resisting this moment greatly. Okay. Now we move to our second part. What is the difference in their stress bending stress? So difference in their maximum bending stress is this one is higher. So 8.4853 M over A cube minus the second one is 6 M over A cube. So you will get this maximum bending stress comes out to be 2.49 M by A cube, which is the answer of our this question. I hope you have enjoyed this video, and that was all about this problem 6-192. If you have any question, you can ask me in comment section, and do subscribe my channel if you are new to it. Thank you for watching and supporting me.